Page 41. The theory of relativity. Mathematics deals exclusively with the relations of concepts to each other without consideration of the relation to experience. Physics too deals with mathematical concepts. However, these concepts attain physical content only by the clear determination of the relation to the object of experience. This in particular is the case for the concepts of motion, space, time. The theory of relativity is that physical theory which is based on a consistent physical interpretation of these three concepts. The name theory of relativity is connected with the fact that motion, from the point of view of possible experience, always appears as the relative motion of one object with respect to another, as of a car with respect to the ground, or the earth with respect to the sun and the fixed stars. Motion is never observable as motion with respect to space, or as it has been expressed as absolute motion. The principle of relativity, in its widest sense, is contained in the statement: the totality of physical phenomena is of such a character that it gives no basis for the introduction of the concept of absolute motion, or shorter but less precise, there is no absolute motion. It might seem that our insight would gain little from such a negative statement. In reality, however, it is a strong restriction for the conceivable laws of nature. In this sense, there exists an analogy between the theory of relativity and the thermodynamics. The latter too is based on a negative statement: there exists no perpetuum mobile. The development of the theory of relativity proceeded in two steps: special theory of relativity and general theory of relativity. The latter presumes the validity of the former as a limiting case, and is its consistent continuation. Alpha, special theory of relativity. Physical interpretation of space and time in classical mechanics. Geometry, from a physical standpoint, is the totality of laws according to which rigid bodies mutually at rest can be placed with respect to each other. The triangle consists of three rods whose ends touch permanently. It is assumed that with such an interpretation the Euclidean laws are valid. Space, in this interpretation, is in principle an infinite rigid body, or skeleton, to which the position of all other bodies is related, body of reference. Analytic geometry, Descartes, uses as the body of reference, which represents space, three mutually perpendicular rigid rods on which the three mutually perpendicular rigid rods on which the coordinates x, y, and z of space points are measured in the known manner as perpendicular projection, with the aid of a rigid unit measure. Physics deal with events in space and time. To each event belongs, besides its place coordinate x, y, z, a time value t. The latter was considered measurable by a clock ideal periodic process of negligible spatial extent. This clock c is to be considered at rest at one point of the coordinate system. Example, at the coordinate origin x equal y equal z equal 0. The time of an event taking place at a point P, x, y, and z is then defined at the time shown on the clock C simultaneously with the event. Here the concept simultaneous was assumed as physically meaningful without spatial definition. This is a lack of exactness which seems harmless only since with the help of light whose velocity is practically infinite from the point of view of daily experience. The simultaneity of spatially distant events can apparently be decided immediately. The special theory of relativity removes this lack of precision by defining simultaneity physically with the use of light signals. The time t of the event in P is the reading of the clock C at the time of arrival of the light signal emitted from the event, corrected with respect to the time needed for the light signal to travel the distance. This correction presumes or postulates that the velocity of light is constant. This definition reduces the concept of simultaneity of spatially distant events to that of the simultaneity of events happening at the same place, the coincidence, namely the arrival of the light signal at C and the reading of C. Classical mechanics is based on Galileo's principles. A body is in rectilinear and uniform motion as long as other bodies do not act on it. This statement can't be valid for arbitrary moving systems of coordinates. It can claim validity only for so-called inertial systems. Inertial systems are in rectilinear and uniform motion with respect to each other, and classical physics laws claim validity only with respect to all inertial systems, special principle of relativity. It is now easy for understand the dilemma which has led to the special theory of relativity. Experience and theory have gradually led to the conviction that light is empty space, always travel with the same velocity c independent of its color and the state of motion of the source of light, principle of the constancy of the velocity of light in the following referred to as Lima principle or L principle. No elementary intuitive considerations seems to show that the same light ray cannot move with respect to all inertial systems with the same velocity c. The Lima principle seems to contradict the special principle of relativity. It turns out, however, that this contradiction is only an apparent one which is based essentially on the prejudice about the absolute character of time, or rather of the simultaneity of distant events. We just saw that x, y, and z and t of an event can, for the moment, be defined only with respect to a certain chosen system of coordinates, inertial system. The transformation of the x, y, z, and t of events which has to be carried out with the passage from one inertial system to another coordinate transformation. It is a problem which can't be solved without special physical assumptions. However, the following postulate is exactly sufficient for a solution. The Lima principle holds for all inertial systems. Application of the special principle of relativity to the Lima principle. The transformations thus defined, which are linear in x, y, z, and t, are called Lorentz transformation. Lorentz transformation are formally characterized by the demand that the expression dx square plus dy square plus dz square minus celerity c square delta t square, which is formed from the coordinate differences dx, dy, dz, dt, or two indefinitely close events, be invariant. That's of the transformation, it goes over into the same expression formed from the coordinate differences in the new system. With the help of the Lorentz transformations, the special principle of relativity can be expressed thus. The laws of nature are invariant with respect to Lorentz transformations A law of nature does not change its form if one introduces into it a new inertial system with the help of a Lorentz transformation on x, y, z, and t. The special theory of relativity has led to a clear understanding of the physical concepts of space and time, and in connection with these, to a recognition of the behavior of moving measuring rods and clocks. It has in principle removed the concept of absolute simultaneity, and thirdly also that of instantaneous action at a distance in the sense of Newton. It has shown how the law of motion must be modified in dealing with motions that are not negligibly small as compared with the velocity of light. It has led to a formal clarification of Maxwell's equations of the electromagnetic field. In particular, it has led to an understanding of the essential oneness of the electric and the magnetic field. It has unified the laws of conservation of momentum and of energy into one single law, and has demonstrated the equivalence of mass and energy. From a formal point of view, one may characterize the achievement of the special theory of relativity thus: it has shown generally the role which the universal constant c, the velocity of light, celerity, plays in the laws of nature, and has demonstrated that there exists a close connection between the form in which time on the one hand and the spatial coordinates on the other hand enter into the laws of nature. B. General theory of relativity. The special theory of relativity, retained the basis of classical mechanics, is one fundamental point, namely the statement: the laws of nature are valid only with respect to inertial systems. The permissible transformations for the coordinates, those which leave the form of the laws unchanged, are exclusively the linear Lorentz transformations. In this restriction rarely founded in physical facts, the following argument convincingly denies it. Principle of equivalence. A body has an inertial mass, resistance to acceleration, and a heavy mass, which determines the weight of the body in a given gravitational field, example that at the surface of the earth. These two quantities, so different according to their definition, are according to experience measured by one and the same number. There must be a deeper reason for this. The fact can also be described thus: in a gravitational field, different masses receive the same acceleration. Finally, it can also be expressed thus: bodies in a field Bodies in a gravitational field behave as in the absence of a gravitational field if, in the latter case, the system of reference used is a uniformly accelerated coordinate system instead of an inertial system. There seems therefore to be no reason to ban the following interpretation of the latter case. One considers the system as being at rest, and considers the apparent gravitational field which exists with respect to it as a real one. This gravitational field generated by the acceleration of the coordinate system would of course be of unlimited extent in such a way that it could not be caused by gravitational masses in a finite region. However, if we are looking for a field-like theory, this fact need not deter us. With this interpretation, the inertial system loses its meaning, and one has an explanation for the equality of heavy and inertial mass. The same property of matter appears as weight or as inertia depending on the mode of description. Considered formally, The admission of a coordinate system which is accelerated with respect to the original inertial coordinates means the admission of nonlinear coordinate transformations, hence a mighty enlargement of the idea of invariance, the principle of relativity. First, a penetrating discussion using the results of the special theory of relativity shows that with such a generalization, the coordinates can no longer be interpreted directly as the results of measurements. Only the coordinate difference, together with the field quantities which describe the gravitational field, determine measurable distance between events. After one has found oneself forced to admit nonlinear coordinate transformation as transformation between equivalent coordinate systems, the simplest demand appears to admit all continuous coordinates transformations which form a group, to admit arbitrary curvilinear coordinate system in which the fields are described by regular functions, general principle of relativity. Now, it is not difficult to understand why the general principle of relativity, on the basis of the equivalence principle, has led to a theory of gravitation. There is a special kind of space whose physical structure field we can presume as precisely known on the basis of the special theory of relativity. This is empty space without electromagnetic field and without matter. It is completely determined by its metric property. Let dx, dy, dz, dt be the coordinate difference of two infinitesimally near points events. Then you find ds square equal dx0 square plus dy0 square plus dz0 square minus célérité carré, célérité square dt0 square, is a measurable quantity which is independent of the special choice of the inertial system. If one introduces in this space the new coordinates x1, x2, x3, x4 through a general transformation of coordinates, then the quantity ds square for the same pair of points has an expression of the form ds square equals sigma, sum or sigma of g sigma g de x g, excuse me, sigma g dx square, no, sigma g1 kilo dx1 dx kilo, summed for e and k from 1 to 4, where g of gtk or gtk égale gkl, de gik or gik égale gkl, the gik which form a symmetric tensor and are continuous functions of x1 to x4, then describe, according to the principle of equivalence, a gravitational field of a special kind, namely one which can be retransformed to the form 1. From Riemann's investigations on metric spaces, the mathematical properties of this GLK field can be given exactly Riemann condition. However, what we are looking for are the equations satisfied by general gravitational fields. It is natural to assume that they too can be described as tensor fields of the type GIK, which in general do not admit a transformation to the form 1, which do not satisfy the Riemann condition, but weaker conditions, which, just as the Riemann condition are independent of the choice of coordinates, are generally invariant. A simple formal consideration leads to weaker conditions which are closely connected with the Riemann condition. These conditions are the very equations of the pure gravitational field on the outside of matter and at the absence of an electromagnetic field. These equations yield Newton's equations of gravitational mechanics as an approximate law, and in addition, certain small effects which have been confirmed by observation. Deflection of light by the gravitational field of a star, influence of the gravitational potential on the frequency of emitted light, slow rotation of the elliptic circuits of planets, perihelion, motion of the planet Mercury. They further yield an explanation for the expanding motion of galactic systems, which is manifested by the redshift of the light emitted from these systems. The general theory of relativity is as yet incomplete, and so far as it has been able to apply the general principle of relativity satisfactorily only to gravitational fields, but not to the total field. We do not yet know with certainty by what mathematical mechanism the total field in space is to be described, and what the general invariant laws are to which this total field is subject. One thing, however, seems certain, namely that the general principle of relativity will prove a necessary and effective tool for the solution of the problem of the total field. The relation energy égale masse factor célérité square, E égale mc carré. In order to understand the law of the equivalence of mass and energy, we must go back to two conservation of balance principles which, independent of each other, held a high place in pre-relativity physics. These were the principle of the conservation of energy and the principle of the conservation of mass. The first of these, advanced by Leibniz as long ago as the 17th century, was developed in the 19th century essentially as a corollary of a principle of mechanics. The drawing from Dr. Einstein's manuscript. We find this drawing. Consider, for example, a pendulum whose mass swings back and forth between the points A and B. At these points, the mass M is higher by the amount H than it is at C. The lowest point of the path, see drawing, at C, on the other hand, the lifting height has disappeared, and instead of it the mass has a velocity v. It is as though the lifting height could be converted entirely into velocity, and vice versa. The exact relation will be expressed as mgh equal m divided by 2 factor v square, with g representing the acceleration of gravity. What is interesting here is that this relation is independent of both the length of the pendulum and the form of the path through which the mass moves. The significance is that something remains constant throughout the process, and that something is energy. At A and at B, it is an energy of position or potential energy. At C, it is an energy of motion or kinetic energy. If this concept is correct, then the sum mgh plus m vector square divided by 2 must have the same value for any position of the pendulum. If h is understood to represent the height above c and v the velocity at that point in the pendulum's path, and such is found to be actually the case, the generalization of this principle gives us the law of the conservation of mechanical energy. But what happens when friction stops the pendulum? The answer to that was found in the study of heat phenomena. This study based on the assumption that heat is an indestructible substance which flows from a warmer to a colder object, seemed to give us a principle of the conservation of heat. On the other hand, from time immemorial, it has been known that heat could be produced by friction, as in the fire-making drills of the Indians. The physicists were for long unable to account for this kind of heat production. Their difficulties were overcome only when it was successfully established that for any given amount of heat produced by friction, an exactly proportional amount of energy had to be expended. Thus did we arrive at the principle of the equivalence of work and heat. With our pendulum, for example, mechanical energy is gradually converted by friction into heat. In such fashion, the principles of the conservation of mechanical and thermal energies were merged into one. The physicists were thereupon persuaded that the conservation principle could be further extended to take in chemical and electromagnetic processes. In short, could be applied to all fields. It appeared that in our physical system there was a sum total of energies that remained constant through all changes that might occur. Now, for the principle of the conservation of mass, mass is defined by the resistance that a body opposes to its acceleration, inert mass. It is also measured by the weight of the body, the heavy mass. That these two radically different definitions lead to the same value for the mass of a body is in itself an astonishing fact, according to the principle, namely, that masses remain unchanged under any physical or chemical changes. The mass appeared to be the essential because unvarying quality of matter, heating, melting, vaporization, or combining into chemical compounds would not change the total mass. Physicists accepted this principle up to a few decades ago, but it proved inadequate in the face of the special theory of relativity. It was therefore merged with the energy principle just as about 60 years before. The principle of the conservation of mechanical energy had been combined with the principle of the conservation of heat. We might say that the principle of the conservation of energy, having previously swallowed up that of the conservation of heat, now proceeded to swallow that of the conservation of mass and holds the field alone. It is customary to express the equivalence of mass and energy, though somewhat inexactly, by the formula E equal mc square, in which c represents the velocity of light about 186,000 miles per second. A is energy that is contained in a stationary body. M is its mass. The energy that belongs to the mass m is equal to this mass multiplied by the square of the enormous speed of light, which is to say, a vast amount of energy for every unit of mass. But if every gram of material contains this tremendous energy, why did it go so long unnoticed? The answer is simple enough. So long as no one of the energy is given off externally, it can't be observed. It is as though a man who is fabulously rich should never spend or given away a cent. No one could tell how rich he was. No, we can reverse the relation and say that an increase of energy in the amount of energy must be accompanied by an increase of energy divided by square celerity, C, in the mass. If can easily supply energy to the mass, for instance, if I heat it by 10 degrees, so why not measure the mass increase of weight increase connected with this change? The trouble here is that in the mass increase, the enormous factor c square occurs in the denominator of the fraction. In such a case, the increase is too small to be measured directly, even with the most sensitive balance. For a mass increase to be measurable, the change of energy per mass unit must be enormously large. Why know of only one sphere in which such amounts of energy per mass unit are released, namely radioactive disintegration? Schematically, the process goes like this. An atom of the mass m splits into two atoms of the mass m square, m prime and m secondo, which separate with tremendous kinetic energy. If we imagine these two masses as brought to rest, that is, if we take this energy of motion from them, then considered together, they are essentially poorer in energy than was the original atom. According to the equivalence principle, the mass sum m prime plus m secondo of the disintegration products must also be somewhat smaller than the original mass m of the disintegrating atom, straight in contradiction to the old principle of the conservation of mass. The relative difference of the two is on the order of 1 divided by 10 of 1%. No, we can't actually weight the atoms individually. However, there are indirect methods for measuring their weight exactly. We can likewise determine the kinetic energies that are transferred to the disintegration products M' and M secondo. Thus, it has become possible to test and confirm the equivalence formula. Also, the law permits us to calculate in advance from precisely determined atom weights just how much energy will be released with any atom disintegration we have in mind. The law says nothing, of course, as to whether or how the disintegration reaction can be brought about. What takes place can be illustrated with the help of our rich man. The atom M is rich. Measure wood during his life gives away no money energy, but in will be bequeaths his fortune to his sons M primo and M secondo, and condition that they give to the community a small amount, less than 1,000 of the whole state energy or mass. The sons together have somewhat less than the father had. The mass sum M primo plus M secondo is somewhat smaller than the mass M of the radioactive atom, but the part given to the community, though relatively small, is still so enormously large, considered as kinetic energy, that it brings with it a great threat of evil. Everything that threat has become the most urgent problem of our time. What is the theory of relativity? I gladly accede to the request of your colleague to write something for the times on relativity. After the lamentable breakdown of the old active intercourse between man of learning, I welcome this opportunity of expressing my feeling of joy and gratitude towards the astronomers and physicists of England. It is thoroughly in keeping with the great and proud traditions of scientific work in your country that eminent scientists should have spent much time and trouble, and your scientific institutions have spared no expense to test the implication of a theory which was perfected and published during the war in the land of your enemies. Even Taft, the investigation of the influence of the gravitational field of the sun on light rays is a purely objective matter. I can't forbear to express my personal thanks to my English colleagues for their work, for without it I could hardly have lived to see the most important implication of my theory tested. We can distinguish various kinds of theories in physics. Most of them are constructive. They attempt to build up a picture of the more complex phenomena out of the materials of a relatively simple formal scheme from which they start out. Thus, the kinetic theory of gases seeks to reduce mechanical, thermal, and diffusional processes to movements of molecules. To build them up out of the hypothesis of molecular motion. When we say that we have succeeded in understanding a group of natural processes, we invariably mean that a constructive theory has been found which covers the process in question. Along with this most important class of theory, there exists a second, which I will call principal theories. These employ the analytic, not the synthetic method. The elements which form their basis and starting point are not hypothetically constructed, but empirically discovered ones. General characteristics of natural processes, principles that give rise to mathematically formulated criteria which the separate processes or the theoretical representation of them have to satisfy. Thus, the science of thermodynamics seeks by analytical means to deduce necessary connections which separate events have to satisfy from the universally experienced fact that perpetual motion is impossible. The advantages of the constructive theory are completeness, adaptability, and clearness. Those of the principal theory are logical perfection and security, or the foundations. The theory of relativity belongs to the latter class. In order to grasp its nature, one needs first of all to become acquainted with the principles on which it is based. Before I go into this, however, I must observe that the theory of relativity resembles a building consisting of two separate stories: the special theory and the general theory. The special theory, on which the general theory rests, applies to all physical phenomena, with the exception of gravitation. The general theory provides the law of gravitation and its relations to the other forces of nature. It has, of course, been known since the days of the ancient Greeks that in order to describe the movement of a body, a second body is needed to which the movement of the first is referred. The movement of a vehicle is considered in reference to the Earth's surface, that of a planet to the totality of the visible fixed stars. In physics, the body to which events are spatially referred is called the coordinate system. The laws of the mechanics of Galileo and Newton, for instance, can only be formulated with the aid of a coordinate system. The state of motion of the coordinate system may not, however, be arbitrarily chosen. If the laws of mechanics are to be valid, it must be free from rotation and acceleration. A coordinate system which is admitted in mechanics is called an inertial system. The state of motion of an inertial system is, according to mechanics, not one that is determined uniquely by nature. On the contrary, the following definition holds good. A coordinate system that is moved uniformly and in a straight line relatively to an inertial system is likewise an inertial system. But the special principle of relativity is meant the generalization of this definition to include any natural event whatever. Thus, every universal law of nature which is valid in relation to a coordinate system C must also be valid as it stands in relation to a coordinate system C', which is in uniform translatory motion relatively to C. The second principle on which the special theory of relativity rests is the principle of the constant velocity of light in vacuum. This principle asserts that light in vacuum always has a definite velocity of propagation and dependent of the state of motion of the observer or of the source of the light. The confidence which physicists place in this principle springs from the successes achieved by the electrodynamics of Clerk, Maxwell, and Lorentz. Both the above-mentioned principles are powerfully supported by experience, but appear not to be logically reconcilable. The special theory of relativity finally succeeded in reconciling them logically by a modification of kinematics, of the doctrine of the laws relating to space and time from the point of view of physics. It became clear that to speak of the simultaneity of two events had no meaning except in relation to a given coordinate system, and that the shape of measuring devices and the speed at which clocks move depend on their state of motion with respect to the coordinate system. But the old physics, including the laws of motion of Galileo and Newton, did not fit in with the suggested relativists' kinematics. From the latter, general mathematical conditions issued to which natural laws had to conform. If the above-mentioned two principles were really to apply, to these physics had to be adapted. In particular, scientists arrived at a new law of motion for rapidly moving mass points, which was admirably confirmed in the case of electrically charged particles. The most important upshot of the special theory of relativity concerned the inert mass of corporeal systems. It turned out that the inertia of a system necessarily depends on its energy content, and this led straight to the notion that inert mass is simply latent energy. The principle of the conservation of mass lost its independence and became fused with that of the conservation of energy. The special theory of relativity, which was simply a systematic development of the electrodynamics of Clerk, Maxwell, and Lorentz, pointed beyond itself. However, should the independence of physical laws of the state of motion of the coordinate system be restricted to the uniform translatory motion of coordinate systems in respect to each other? What has nature to do with our coordinate system and their state of motion? If it is necessary for the purpose of describing nature to make use of a coordinate system arbitrarily introduced by us, then the choice of its state of motion ought to be subject to no restriction. The laws ought to be entirely independent of this choice general principle of relativity. The establishment of this general principle of relativity is made easier by a fact of experience that has long been known, namely that the weight and the inertia of a body are controlled by the same constant, equality of inertial and gravitational mass. Imagine a coordinate system which is rotating uniformly with respect to an inertial system in the Newtonian manner. The centrifugal forces which manifest themselves in relation to this system must, according to Newton's teaching, be regarded as effects of inertia, but the centrifugal forces are exactly like the forces of gravity, proportional to the masses of the bodies. Ought it not to be possible in this case to regard the coordinate system as stationary and the centrifugal forces as gravitational forces? This seems the obvious view, but classical mechanics forbade it. This hasty consideration suggests that a general theory of relativity must supply the laws of gravitation, and the consistent following up of the idea has stifled our hopes. But the path was thornier than one might suppose because it demanded the abandonment of Euclidean geometry. This is to say, the laws according to which fixed bodies may be arranged in space do not completely accord with the spatial laws attributed to bodies by Euclidean geometry. This is what we mean when we talk of the curvature of space. The fundamental concepts of the straight line, the plane, etc., terribly lose their precise significance in physics. In the general theory of relativity, the doctrine of space and time, or kinematics, no longer figures as fundamental and independent of the rest of physics. The geometrical behavior of bodies and the motion of clocks rather depend on gravitational fields, which in their turn are produced by matter. The new theory of gravitation diverges considerably as regards principles from Newton's theory, but its practical results agree so nearly with those of Newton's theory that it is difficult to find criteria for distinguishing them which are accessible to experience. Such have been discovered so far in the revolution of the ellipses of the planetary orbits round the Sun, confirmed in the case of Mercury. 2. In the curving of light rays by the action of gravitational field, confirmed by the English photographs of eclipses. 3. In the displacement of the spectral lines towards the red end of the spectrum in the case of light transmitted to us from stars of considerable magnitude, unconfirmed so far. The chief attraction of the theory lies in its logical completeness. If a single one of the conclusions drawn from it proves wrong, it must be given up to modify it without destroying the whole structure seems to be impossible. Let no one suppose, however, that the mighty work of Newton can really be superseded by this or any other theory. His great and lucid ideas will retain their unique significance for all time as the foundation of our whole modern conceptual structure in the sphere of natural philosophy. Note, some of the statements in your paper concerning my life and person owe their origin to the lively imagination of the writer. Here is yet another application of the principle of relativity for the delectation of the reader. Today, I am described in Germany as a German savant and in England as a Swiss Jew. Should it ever by my fate to be represented as a bête noire, I should, on the contrary, become a Swiss Jew for the Germans and a German savant for the English. Physics and reality. It has often been said, and certainly not without justification, that the man of science is a poor philosopher. General consideration concerning the method of science. Okay. Why then should it not be the right thing for the physicist to let the philosopher do the philosophizing? Such might indeed be the right thing at a time when the physicist believes he has at his disposal a rigid system of fundamental concepts and fundamental laws which are so well established that waves of depth cannot reach them. But it cannot be right at a time when the very foundations of physics itself have become problematic as they are now. At a time like the present, when experience forces us to seek a newer and more solid foundation, the physicist can't simply surrender to the philosopher the critical contemplation of the theoretical foundations, for he himself knows best and feels more surely where the shoe pinches. In looking for a new foundation, he must try to make clear in his own mind just how far the concepts which he uses are justified and are necessities. The whole of science is nothing more than a refinement of everyday thinking. It is for this reason that the critical thinking of the physicist can't possibly be restricted to the examination of the concepts of his own specific field. He can't proceed without considering critically a much more difficult problem, the problem of analyzing the nature of everyday thinking. On the stage of our subconscious mind appear in colorful succession sense experiences, memory pictures of them, representation and feelings. In contrast to psychology, physics treats directly only of sense experiences and of the understanding of their connection. But even the concept of the real external world of everyday thinking rests exclusively on sense impressions. Now, we must first remark that the differentiation between sense impressions and representation is not possible, or at least is it not possible with absolute certainty. With the discussion of this problem, which affects also the notion of existence of sense experiences as given, that is to say, as psychic experiences of special kind. I believe that the first step in the setting of a real external world is the formation of the concept of bodily objects and of bodily objects of various kinds. Out of the multitude of our repeatedly occurring complexes of sense impression, partly as scenes for sense experiences or of others, and we attribute to them a meaning. The meaning of the bodily object. Considered logically, this concept is not identical with the totality of sense impressions referred to, but it is an arbitrary creation of the human or animal mind. On the other hand, the concept owes its meaning and its justification exclusively to the totality of the sense impressions which we associate with it. The second step is to be found in the fact that in our thinking, which determines our expectation, we attribute to this concept of the bodily object a significance which is to a high degree independent of the sense impression which originally gives rise to it. This is what we mean when we attribute to the bodily object a real existence. The justification of such a setting rests exclusively on the fact that, by means of such concept and mental relation between them, we are able to orient ourselves in the labyrinth of sense impressions. These notions and relations, although free statements of our thoughts, appear to us as stronger and more unalterable than the individual sense experience itself, the character of which as anything other than the result of an illusion or hallucination is never completely guaranteed. On the other hand, these concepts and relations, and indeed the setting of real objects, and generally speaking the existence of the real world, have justification only in so far as they are connected with sense impressions between which they form a mental connection. The very fact that the totality of our sense experiences is such that by means of taking operation with concepts and the creation and use of the finite functional relations between them and the coordination of sense experiences to this concept, it can be put in order. This fact is one which lives us in a way, but which we shall never understand. One may say the eternal mystery of the world is its comprehensibility. It is one of the great realizations of Immanuel Kant that the setting up of a real external world would be senseless without this comprehensibility. In speaking here concerning comprehensibility, the expression is used in its most modest sense. It implies the production of some sort of order among sense impressions. This order being produced by the creation of general concepts, relation between these concepts and by relation between the concepts and sense experience. These relations being determined in any possible manner. It is in this sense that the world of our sense experiences is comprehensible. The fact that it is comprehensible is a miracle. In my opinion, nothing can be said concerning the manner in which the concepts are to be made and connected, and how we are to coordinate them to be experiences, in guiding us in the creation of such an order of sense experiences. Success in the result is alone the determining factor. All that is necessary is the statement of a set of rules, since without such rules the acquisition of knowledge in the desired sense would be impossible. One may compare these rules with the rules of a game in which, while the rules themselves are arbitrary. It is the rigidity alone which makes the game possible. However, the fixation will never be final. It will have validity only for a special field of application. There are no final categories in the sense of Kant. The connection of the elementary concepts of everyday thinking with complexes of sense experiences can only be comprehended intuitively, and it is unadaptable to scientifically logical fixation. The totality of these connections, none of which is expressible in notional terms, is the only thing which differentiates the great building, which is science, from a logical but empty shame of concepts. By means of this connection, the purely emotional theorems of science become statements about complexes of sense experiences. We shall call primary concepts such concepts as are directly and intuitively connected with typical complexes of sense experience. All other notions are from the physical point of view possessed of meaning only in so far as they are connected by theorems with the primary emotions. These statements derived logically from them and partially theorems not derivable from the definitions, which express at least indirect relations between the primary concepts and in this way between sense experiences. Theorems of the latter kind are statements about reality or laws of nature. Theorems which have to show their usefulness when applied to sense experiences comprehended by primary concepts. The question as to which of the theorems shall be considered as definitions and which as natural laws will depend largely upon the chosen representation. It really becomes absolutely necessary to make this differentiation only when one examines the degree to which the whole system of concepts considered is not empty from the physical point of view. The stratification of the scientific system. The aim of science is on the one hand a comprehension as complete as possible of the connection between the sense experience in their totality, and on the other hand the accomplishment of this aim by the use of a minimum of primary concepts and relations, seeking as far as possible logical unity in the word picture, a paucity in logical elements. Science concerns the totality of the primary concepts here, concepts directly connected with sense experiences, and theorems connecting them in its first stage of development. Science does not contain anything else. Our everyday thinking is satisfied on the whole with this level. Such a state of affairs can't, however, satisfy a spirit which is really scientifically minded, because the totality of concepts and relations obtained in this manner is utterly lacking in logical unity. In order to supplement this deficiency, one invents a system poorer in concepts and relations, a system retaining the primary concepts and relations of the first layer as logical derived concepts and relations. This new secondary system pays for its higher logical unity by having as its own elementary concepts of the second layer only those which are no longer directly connected with complexes of sense experiences. Further, striving for logical unity brings us to a tertiary system still poorer in concepts and relations, for the deduction of the concepts and the relations of the secondary, and so indirectly of the primary. layer. Thus, the story goes on until we have arrived at a system of the greatest conceivable unity and of the greatest poverty of concepts, of the logical foundations, which are still compatible with the observation made by our sense. We do not know whether or not this ambition will ever result in a definite system. If one is asked for his opinion, he is inclined to answer no. We're wrestling with the problems. However, one will never give up the hope that this greatest of all aims can really be attained to a very high degree. An adherent to the theory of abstraction or induction might call our layers degrees of abstraction, but I do not consider it justifiable to weigh the logical independence of the concept from the sense experiences. The relation is not analogous to that of soup to beef, but rather of wardrobe number to overcoat. The layers are furthermore not clearly separated. It is not even absolutely clear which concepts belong to the primary layer. As a matter of fact, we are dealing with freely formed concepts which, with a certainty sufficient for practical use, are intuitively connected with complexes of sense experiences in such a manner that, in any given case of experience, there is no uncertainty as to the applicability or no applicability of the statement. The essential thing is the aim to represent the multitude of concepts and theorems close to experience as theorems logically deduced and belonging to a basis as narrow as possible of fundamental concepts and fundamental relations which themselves can be chosen freely. Axioms. The liberty of choice, however, is of a special kind. It is not in any way similar to the liberty of a writer of fiction. Rather, it is similar to that of a man. Rather, it is similar to that of a man engaged to solving a well-designed word puzzle. He may, it is true, propose any word as the solution, but there is only one word which really solves the puzzle in all its forms. It is an outcome of fate that nature, as she is perceptible in our five senses, takes the character of such a well-formulated puzzle. The successes reaped up to now by science do, it is true, give a certain encouragement for this fate. The multitude of layers discussed above corresponds to the several stages of progress which have resulted from the struggle for unity in the course of development. As regards the final aim, intermediary layers are only of temporary nature. They must eventually disappear as irrelevant. We have to deal, however, with the science of today, in which these strata represent problematic partial successes, which support one another but which also threaten one another. Because today's system of concepts contain deep-seated incongruities which we shall meet later on. It will be the aim of the following lines to demonstrate what path the constructive human mind has entered. In order to arrive at the basis of physics, which is logically as uniform as possible, to mechanics and the attempts to base all physics upon it. An important property of our sense experiences and more generally of all our experience is its time-like order. This kind of order leads to the mental conception of a subjective time and ordinating shame for our experience. The subjective time leads then through the concept of the bodily object and of space to the concept of objective time, and we shall see later on ahead of the notion of objective time there is, however, the concept of space, and ahead of the latter we find the concept of the bodily object. The latter is directly connected with complexes of sense experiences. It has been pointed out that one property which is characteristic of the notion bodily object is the property which provides that we coordinate to it an existence independent of subjective time and independent of the fact that it is perceived by our sense. We do this in spite of the fact that we perceive temporal alterations in it. Poincaré has justly emphasized the fact that we distinguish two kinds of alterations of the bodily object, changes of state and changes of position. The latter, he remarked, are alterations which we can reverse by arbitrary motions of our body, that they are bodily objects to which we have to ascribe. Within a certain sphere of perception, no alteration of state, but only alterations of position, is a fact of fundamental importance for the formation of the concept of space, in a certain degree even for the justification of the notion of the bodily object in itself. Let us call such an object practically rigid. If as the object of our perception, we consider simultaneously as a single unit two practically right bodies, then there exist for this ensemble such alterations as cannot possibly be considered as changes of position of the whole, notwithstanding the fact that this is the case for each one of the two constituents. This leads to the notion of change of relative position of the two objects, can in this way also to the notion of relative position of the two objects. It is found, moreover, that among the relative position there is one of a specific kind which we designate as contact. Permanent contact of two bodies in three or more points means that they are united as a quasi-rigid compound body. It is permissible to say that the second body forms then a quasi-rigid continuation on the first body, and many, in its turn, be continued quasi-rigidly. The possibility of the quasi-rigid continuation of a body is unlimited. The real existence of the conceivable quasi-rigid continuation of a body, BO, is the infinite space determined by it. In my opinion, the fact that every bodily object situated in any arbitrary manner can be put into contact with the quasi-rigid continuation of a determined and chosen body, B, body of relation. This fact is the empirical basis of our conception of space. The pre-scientific thinking, the solid Hertz crust, plays the role of B and its continuation. The very name geometry indicates that the concept of space is psychologically connected with the Hertz as an assigned body. The body notion of space, which preceded all scientific geometry, transformed our mental concept of the relations of position of bodily objects into the notion of the position of this bodily object in space. This of itself represents a great formal simplification. Through this concept of space, one reaches, moreover, an attitude in which any description of position is admittedly a description of contact. The statement that a